departure from the earlier theory of gravity that existed until now, just due to Newton. According to Einstein's theory, gravity is a manifestation of the curvature of space-time. So any massive objects or other forms of energy like electromagnetic energy would curve the space and time around it. In fact, we also learned from Einstein's earlier theory of relativity, which is a special theory of relativity, that the space and time are not independent entities, but they are all part of a single entity called the space-time. And in the absence of gravity or any massive objects or other forms of energy, the space-time is completely flat, and the geometry is described by a simple extension of the Euclidean geometry that we all learn in school. But for example, in the presence of a massive object, in the vicinity of a massive object, this geometry of Euclid ceases to be valid, and one has to use an extension or a generalization of those calculations, which was due to Riemann, etc. So if you think of in physical terms, very, very far away from massive objects, or in the absence of gravity, space-time is completely flat. So one could actually verify its flatness by, for example, drawing a triangle and adding the angles inside the triangle, and you will get 180 degrees. But if you repeat the same exercise in the vicinity of a massive object, and if you have a precise enough measurements, and if you add the angles inside a triangle, they won't add up to 180 degrees. So, although this is rather like a thought experiment, one could actually think of real physical manifestation of the curvature of space-time that manifest in various kinds of astronomical observations as well as daily life. So one such remarkable observational prediction of Einstein's theory is that gravity bends light. So we know from our usual experience, day-to-day experience, that light travels through straight line. And that's because the shortest distance between 2 points in a flat space is a straight line. And when the space-time is curved in the presence of a massive object, the shortest distance between 2 points is not a straight line. The generalization of that is called a geodesics. Mathematicians call it geodesics. And light basically travels through geodesics of that space-time. And if, for example, this is my cartoon of the space-time curved by the sun, and if there is a distant star whose rays are grazing the limb of the sun, in the vicinity of the sun's gravitational field or curved space-time, light travels to the geodesics of this curved space-time. So the observer who is looking from the other end would see a shift in the position of the star. So this, since we know the mass of the sun as well as the original location of the star, one could actually calculate the expected shift in the apparent position of the star when the star's rays are grazing the limb of the sun. And in the beginning of 20th century, 1919, during a total solar eclipse, a team of, in fact, 2 teams of astronomers led by Arthur Eddington, the British astronomer and physicist Arthur Eddington, set forward to observe the gravitational bending of light from distant star during this eclipse. So this eclipse was observable from mostly from the southern hemisphere. So they sent 2 teams, one to Africa in the island of Principe, which is in the west coast of Africa, and another team also went to Brazil also. So this is a location of the island Principe in the west coast of Africa. And in the middle, I show one of the actual photographic plates taken by Eddington's team during this eclipse. If you squint very, very carefully, you would see the stars, but it's rather hard to see that. So I've made a cartoon version of this. This is a cartoon version of what Eddington and his colleagues observed during this eclipse. So what they observed, basically during this eclipse, this sun was basically aligned with a cluster of star called the Hyades cluster. It is in the constellation Taurus, the bull, and they observed basically the position of the star during the eclipse, which is shown by these red stars in this cartoon. And after a few months, they observed the same cluster of stars in the night sky, and the sun was not in between us and them. And that is like a reference location of these stars, which is shown by these blue stars here. And then you can very clearly see, if you align them, you could clearly see that the angular position of these stars have shifted during the eclipse. And according to Einstein's theory, this angle of angular shift can be calculated to be equal to 4 gm by rc square, where g is the Newton's constant and c is the speed of light and m is the mass of the sun, and r is the location of the star measured from the center of the sun. And for example, if for a star whose rays are grazing the limb of the sun, this predicted angular shift is of the order of it's like 1.75 arc second. The Newtonian theory of gravity, one could also derive an angular shift like this, but the conceptual interpretation is a bit problematic. But even if you do this a calculation, the predicted angular shift is only half of this. So the question was whether the observed whether there was any shift in the angular position of stars during the eclipse, and if yes, whether it matches better with Einstein's theory or Newton's theory. And it turns out that these observations are consistent with Einstein's theory, which made a huge amount of news when Eddington and his colleagues announced the results of this observations in a Royal Society's meeting in November 1919. So this was reported all over the world, made Einstein a celebrity internationally almost overnight. For example, in the right side is a front page of the New York Times, and the headline says, "Lights all askew in the heavens, and Einstein's theory triumphs," etc. It also says like stars were not where they seem to be, but nobody needs to worry, etc. It made this news not only in the Western world. In the left-hand side is a article written by Meghna Saha at the Calcutta newspaper, The Statesman, where Saha very emphatically states that if this Eddington's observation this would completely change our perception of space and time. This Einstein's theory that predicts this completely revolutionize our understanding of space and time, and that's what happened in the last century. Now we know that our understanding of space and time has changed in a revolutionary science theory. And now these gravitational bending of light is a very commonplace phenomenon in astronomy. In fact, there are very, very dramatic versions astronomers routinely make, especially in the last few decades. And these are called gravitational lenses. Basically, very, very massive objects like galaxies or clusters of galaxies basically curve their space-time around them so strong that the light from distant stars and distant galaxies are focused by the presence of this gravitational lens, and we could see sort of even multiple images of the same source due to this lensing effect. So here is a cartoon version of this. We are on the bottom left corner, the Earth, and there is a distant galaxy at the top right corner. And in between us and this distant galaxy, there is another galaxy, which is very massive, and it curves the space-time around it. And light from this background galaxy can come towards us through multiple paths because of the curvature of space-time. And these multiple paths, we can get to see multiple images of the same source. This is like an extreme example of gravitational lensing, and there are gravitational lensing comes in many forms. For example, strong, weak, or micro, like good, bad, and ugly. So these are some real examples of how the gravitational lensing would appear in these circumstances. For example, in the leftmost plot is an actual image of a quasar, a very distant quasar, which is lensed by another galaxy or a cluster in between us and this distant quasar. And because of the geometry of the lens, it turned out that you form 4 images of this lens. So this is called strong lensing. So, for example, if the projected mass density of the lens is greater than a certain critical density, it can produce multiple images. This lens can produce multiple images of the source. And the left-hand side shows such a quadrupled image, quadruply lensed image of a distant quasar. I think this is an X-ray observation, if I'm not mistaken. And the middle plot is what is called an example of a weak lensing. Here, the projected mass density to our line of sight or to the plane perpendicular line of sight is not that large. It is less than a certain critical density. Then the lensing is not strong enough to produce multiple images. So what instead it does is to distort the shape of the background objects. And here you can see certain very characteristic arc shapes, which are basically usually looking spiral or elliptical galaxies in the background, distorted by the lensing potential of a foreground lens, which is creating a cluster galaxies. And by studying the distortion of the lens, and if you assume certain statistical properties of the shape of the background galaxies, one could actually infer the mass potential, the potential or the mass distribution of the lens that is causing these distortions. This is like analogous to the kind of ripple pattern that you would see in a swimming pool. So, for example, if you have a swimming pool that has a very regular grids, and when the water is moving, water is making waves on the swimming pool, you would see that this background grid get distorted. And if you know exactly the geometry of this background grid, you can actually calculate the shape of the waves. In principle, if you know the refractive index of water, etc. Similarly, you can. This is the way we, astronomers sort of solve this inverse problem of computing the lensing potential from the distorted image of galaxies. In practice, you do not know the actual shape of background galaxies, but if you make some statistical assumptions that the shapes are, galaxies are isotropically distributed, there are no preferred directions, etc., one could statistically infer the presence of such weak lensing, which has become a really powerful tool to map out mass distributions in the universe, because the lensing does not care whether the mass is luminous or dark. So lensing has now become a very powerful tool to map out the distributions of dark matter in the universe. Another very interesting example of lensing is the so-called micro lensing, where the lens mass is very, very small, so that the critical density it's much smaller. The density is also very, very small, so that it cannot produce any significant magnification in general, as well as multiple images certainly. But if, for example, the lens somehow comes in front of a background source, then you would see a sudden increase in the magnification to the distant source. So one example is, for example, if you're looking at a distant star for a long time, and if some other object, like a star or a black hole or a planet or something like that, comes in between us and the distant star, then that micro lensing effect of that lens would focus light from the distant star, and would increase the observed flux for a part of the time during this transit. So you would see this characteristic pulse that is a telltale signature of the microlensing. And this is now a really powerful tool now to, for example, detect, for example, the presence of, for example, black holes or exoplanets, planets outside the solar system, etc. So in the last few decades, gravitational lensing has emerged to be a really powerful tool for astronomical and cosmological explorations. So I'm giving a few examples of the power of gravitational lensing. Gravitational lensing has been used to um, um, gather evidence of dark matter. So here is one very famous example in the top panel. So as I told earlier, by studying the weak lensing distortions of galaxies, one could actually map out the mass distribution of the lens that is causing these distortions. So here is the top left plot such estimation of the mass distribution of a lensing cluster. This is called the so-called bullet cluster, and these green contours are where the masses are concentrated in this cluster of galaxies. So where the contour lines are closer, the mass is the largest, as the usual interpretation of contour plots. But now, if you look at this cluster using X-rays, which is the right plot, it turns out that the luminous part of this cluster is not where the mass is concentrated. So the luminous part is shown by these yellow and white regions. And you can see a very visible offset between the luminous part of this cluster of galaxies and the massive part of this cluster of galaxies. So the conclusion is that most of the part of this cluster, most of the mass of the cluster is in the form of dark matter, which has an offset from where the luminous part is. But roughly, if you look at the very cosmological scale, cosmologists can see that by looking at much larger fields. These dark matter potentials essentially serve as sort of seeds, potential wells where the baryonic matter accumulates and eventually form galaxies and et cetera, et cetera. And similarly, doing this for a large number of galaxies, both strong lensing as well as weak lensing, one could map out such mass distribution of dark matter in the universe, and this is some very strong observational evidence suggesting that a significant fraction of of the mass in the universe is in the form of dark matter. It has some diffuse sort of thermal distribution also. Also, interestingly, gravitational lensing once in a while can provide some very, very magnified images and stars. So it's like having a magnifying glass to look at some objects. So you can see them much brighter and with much better magnification. So some of the very, very distant galaxies, which could not have been observed otherwise, are now we are able to observe them purely because of this magnification provided by gravitational lens. So you also know that distance in cosmology, astrophysics, means that these objects were also coming from earlier in the history of the universe. So these stars, or these galaxies and stars, are also the first or early galaxies and early stars in the cosmological history. So lensing, because of this extra magnification, provides us a way of studying the first stars and galaxies because of this extra magnification. There were some really extreme examples observed in the last few years. One is the observation of a star at a distance of about 9 billion light years, because it got magnified by some 2,000 times due to a cluster which happens to be in between the star and us. So it is very, very rare to see stars from such large cosmological distances, but lensing provides some ways of observing. I told you that lensing provides a very, very neat way of identifying dark matter and to map out its distribution. But also lensing, microlensing, for example, is used to identify or constrain at least the nature of dark matter also. Just to take one step back, we know through a variety of astronomical and cosmological observations that about 25% of the total mass energy in the universe is in the form of what is called dark matter. We cannot see it, but we can see its influence, its gravitational influence on other luminous objects like motion of stars and etc. That's why we know the dark matter exists. But it is not entirely clear what is the constitution of dark matter. So one most popular belief is that dark matter is comprised of some particles, some fundamental particles, which are beyond the standard model of particle physics. And there are a number of such experiments going on to identify such dark matter particles colliding and probably producing some observational signatures. But none of them have found any evidence, any serious evidence so far. Another possibility is that the dark matter could be comprised of a large number of compact objects, like small black holes or planets or any object that doesn't emit light but has some mass and hence produce gravity. And if that is the case, these are called compact dark matter or machos. If that is the case, if you, for example, look at a distant, like in our neighboring galaxy, several stars in our neighboring galaxy, through the dark matter halo of our galaxy, because the dark matter is much more diffuse than ordinary baryonic matter and has a much larger spatial extent. And if you look at the neighboring galaxy through this dark matter halo, then you should see that once in a while, some of these compact objects would come in between us and stars in the neighboring galaxy and produce a microlensing effect, which is like a time-dependent increase in the magnification. So you could either detect the presence of such compact object, or the absence of such detection can put an upper limit on the fraction of dark matter that is contributed by these compact objects. So it's a powerful way of constraining this hypothesis that dark matter could be due to compact objects like primordial black holes and similar kinds of objects. The same principle can also be used to detect planets outside the solar system. Again, there is a very interesting telltale signature of planetary system. So the bottom right plot is a cartoon of an sort of extension of what I showed in the previous slide of a microlensing observation. So there is a yellow star at the top. It's a distant star, and there is another star that comes in between us, which is we are at the bottom, and the source, which is at the top. And you should see this increased magnification, increased flux due to the magnification caused by this transiting star, just this sort of pulse shape. But now if this star, this lens star, also has a planetary system around it, then this little planet should cause some additional lensing effect on top of the lensing effect caused by the star. So you would see on the right side, you would see an extra blip on top of this pulse that is contributed by the lensing of the star. So such lensing observation has been used to identify extrasolar planets, exoplanets, and dozens of such planets have been observed from the data of the Kepler satellite using microlensing observation. So there has been a number of such uses of gravitational lensing, and it has become one of the most powerful tools for astronomers and cosmologists in the last few decades. And let me switch gears now. Just like the gravitational bending of light was originally thought of as a way of testing Einstein's theory and has now become a powerful tool for astronomical exploration, a new tool for astronomical observation was available to us in the last 5 years to the detection of gravitational waves. And the existence of gravitational waves also was predicted by Einstein's theory of general relativity. And gravitational waves are wave-like solutions to Einstein's equations, mathematically speaking. And they can be thought of as oscillations or disturbances that are propagating on the geometry of space-time. So any massive object that moves with an acceleration would produce these ripples in space-time. And as they propagate and reach us, they change the geometry of the space-time that we live in. They produce distortions in our space-time, which can be measured using very precise detectors, which are called laser interferometers. And in the last 5 years, the LIGO observatories, as well as its sister observatory called Virgo, have observed dozens of such gravitational wave signals coming from colliding black holes and colliding neutron stars at different parts of the universe. And we are basically, with these observations, we are opening up a new branch of observational astronomy. So here, for example, is a catalog of the gravitational wave sources that we have detected in the last 5 years. So the vertical axis is the mass of these compact objects in binary systems. These are gravitational waves are produced by motions of two compact objects, which could be black holes or neutron stars, in a binary system. So they move at very, very fast velocities, comparable to the speed of light eventually. And these disturbances produce oscillations in space-time, which propagate outwards. And they take away energy from this orbit. And as a result, the orbit come closer and closer. So these objects spiral inwards, eventually merging with each other, producing a more massive compact object, which is most of the time a black hole, which is rapidly spinning also. So these vertical axis shows the mass of these compact objects in the binary system in units of solar masses. So one is the mass of the sun, and 160 is 160 times the mass of the sun. So each of these mergers basically involves three objects. You start with two objects, two black holes or two neutron stars orbit around, and finally they merge to form a much more massive object, which is mostly a black hole. So you can see this, each cluster connects two dots to one more massive dot. And these blue dots are the black holes discovered by LIGO and Virgo. And if you compare them against the black hole candidates discovered by X-ray observations from our own galaxy, and these are from what is called X-ray binaries, where one star is orbiting a black hole, and by studying the emission of the accreting gas from the star, X-ray astronomers can measure the mass of the black holes. And it turns out that the mass of the LIGO black holes are the LIGO black holes are much more massive than the black holes in our own galaxy. So this was a surprise to most astronomers, that there are these new populations of heavy black holes that exist in the universe. Similarly, we also have a few observations of merging neutron stars, and there are some one mystery object also, which is not one object it is not clear whether it is a black hole or a neutron star. It could either be the most massive neutron star observed or the least massive black hole observed. So, and we have currently no way of telling between them. In either way, it's a surprise object. And so these observations are really opening up a new way of observing the universe. And as we speak, we have more data coming up, being analyzed, and we expect to see many more signals in the next few months. So these observations have produced some very, very interesting science. So, for example, these are the first observations of merging binary black holes. As I mentioned, they provided the evidence of stellar mass black holes that are much more massive than the kind of black hole we have seen before, more than 30 solar masses. There are some potential evidence of what is called the intermediate mass black holes, which are black holes more massive than about 100 solar masses, but less massive than about 10,000 solar masses or so. And these LIGO and Virgo made a very remarkable observation of a merger of two neutron stars. And we not only observed the gravitational waves from them, we also observed the electromagnetic counterparts of this merger through a variety of astronomical observations, electromagnetic telescopes, starting from gamma rays and all the way up to radio. And there are many, many additional event candidates coming up. And in particular, this very exciting and mysterious object, which is from this binary GW 190814, which is named after the date of its observation. It is either the lightest black hole ever observed or the heaviest neutron star ever observed. So I encourage you to read these very accessible science summaries of all the LIGO Virgo papers, which are accessible from the LIGO Virgo webpage, and apart from the actual publications in the LIGO Virgo scientific collaboration. So, and it is important for us to remind ourselves that the gravitational wave astronomy has only begun. It is just beginnings, the first steps of this new branch of astronomy. These observatories like LIGO and Virgo have not yet reached their design sensitivities, and each small improvement in their sensitivity will actually gain us a significant increase in the event rate, in the volume of universe that we are able to observe, and hence event rate. And if you just extrapolate the projected increase in the sensitivity of these observations and our understanding of the rate of such merger events happening in the universe, in the local universe, we can safely predict that in the next few years, we will be observing several hundreds of compact binary mergers using LIGO and Virgo. And this could even lead to several thousand. And these would provide a number of very, very interesting probes of fundamental physics, astrophysics, and cosmology. I don't want to go to the details, but there are some very, very interesting questions that are that modern astronomers and cosmologists and fundamental physics ask. And gravitational observations could provide some very interesting constraints, or in the best case, some answers to these puzzles. And from an observational point of view, the one very interesting thing that we from the Indian community are excited about is the ongoing program to build a LIGO observatory in India called the LIGO India, which has a target operation of beyond 2026 or so. And this would enable us to be part of a major frontier of science in the next decade. So one such frontier, in my personal opinion at least, is the gravitational lensing of gravitational waves. So it turns out that according to Einstein's theory, gravitational waves are bent or lensed exactly in the same way as electromagnetic waves. And if you fold in our expected detection rates and our sensitivities and the distribution of lenses in the universe, such as galaxies and galaxy clusters, it turns out that a small fraction of the gravitational waves that we observe in the next several years would be lensed by intervening galaxies and sometimes clusters also. It's a small fraction. That fraction is of the order of 0.1% to 0.5%. But because we are expecting several hundreds and possibly several thousands of events in the next few years, we expect by pure statistics that a few of such events would be gravitationally lensed by intervening matter, like clusters or galaxies. So this is very interesting, and just like we have seen these multiple images of quasars, etc., we will also see multiple images of these gravitational wave events. So here is a right-hand side is a cartoon. So there is a merge that is happening at a distant galaxy, and on the other side is the LIGO Virgo detectors, and there is a galaxy in between us and the source. And because of the curvature of the space-time, there are multiple paths, multiple geodesics connecting us and the source, and then that's how we get these multiple images. And unfortunately, the image separation the angular separation of multiple images, which is of the order of gm by c square r, we discussed, is of the order of arc seconds. And this kind of resolution is resolvable using electromagnetic telescopes, but unfortunately, gravitational wave observatories have very poor angular resolution. So these angular separation is not something that these gravitational observatories can resolve. But they can resolve some very interesting other things. You can resolve them temporarily, because these merger events are transient signals. They last only for a fraction of a second to a few seconds in the frequency band of gravitational wave observatories. And these lensing produces a time delay between multiple images or multiple paths. And these time delays could be anywhere between minutes to hours, or sometimes even weeks also. So what you should see is, once gravitational wave signal would arrive first, and after several minutes or several days or several weeks, a copy of the same gravitational wave signal would arrive second. This is something rather difficult to observe in electromagnetic observations. Although there are similar examples of that been observed so far, like an exploding supernova has been observed in a lensed image. So, 100 years after Eddington's observation of the bending of light, we are expecting the gravitational bending of gravitational waves. And this can have some very interesting implications. So just like the magnification produced onto light, gravitational waves also magnified in the same way. So for example, the polarization, so most of the dominant contribution to the lens is from the galaxies. And here, because of the mass or the gravitational length scale of the lens is so large as compared to the wavelength of gravitational waves, you can treat them in pure geometric optics or ray optics calculations. And the only effect on this lens is the magnification. So it doesn't, for example, affect the shape of the signal. So here's some cartoon example of two sort of copies of gravitational waves, the relative magnification. So you can see that the second image is a demagnified version of the first image. And that magnification factor is given by the square root of mu. And once in a while, you can get some really high magnification in the lensed images, which should act as sort of cosmic magnifying glasses, which should allow you to see very, very distant sources which would not have been observable otherwise. So here is an actual, left-hand side is an actual example of such an highly magnified image of a star using electromagnetic observations to optical observations. So there's the left pole plot is a cluster of galaxies, which is acting as a lens. And the right-hand side, there is in the bottom right, there is a little dot at the tip of the arrow. It's a star. It's a star that 9 billion light years, which is a hopelessly distant star in usual standards of astronomy. So for example, if few astronomers looked at the same patch in 2011, they could not see any trace of the star. But after 5 years, because of the relative motion between the star and this cluster lens, there was a cosmic alignment, and that magnified the star, which made it visible in 2016. So similar, the same thing can happen in gravitational waves also. So we have not observed it yet, but using theoretical calculations, we could actually predict how far you can see because of this lensing effect. So here is on the right-hand side is an estimation. So typically the gravitational observatories have some horizon beyond which we cannot see gravitational sources, and that horizon is depending on the mass of the source of gravitational waves, the black hole binaries, for example, because the more massive a binary, the louder is the gravitational wave signal. So that's why typically you have, so this green plot here is the horizon distance as a function of the total mass for the binary black hole system for the advanced LIGO detector. So all these binaries sort of before or with redshifts less than or distances less than this horizon distance will be observed using LIGO, and nothing outside, nothing above this horizon distance will be visible. But because of the lensing magnification, you can see a fraction of these events outside this horizon distance also, and that is shown by these yellow regions. So here, these color contours shows the number of events detectable by LIGO. Red means larger, yellow is intermediate, and blue is sort of 0. So this extra region, yellow region above the green line, is this new population of sources that has contributed to our observational sample by lensing. And this could also, in the case of these stars, one can actually accurately estimate the distance to the source because of the spectral signatures of various lines in the stars. So one could do a spectroscopic measurement, and that would give us a cosmological redshift. But unfortunately, in the case of gravitational waves, there are no such spectral lines, and there are no characteristic frequencies also. And all frequencies are scalable with mass. So our measurement of distance is based on some kind of standard candle. So we can measure the mass of the system from its frequency evolution of the signal, and if you know the mass of the signal, you can calculate its absolute brightness or absolute amplitude. And since we measure the apparent amplitude or the apparent brightness, they are related by the luminosity distance or the square of luminosity distance in the case of flux. That's how we are estimating the distance. But now if the lensing basically magnifies a star or a binary black hole, it basically appears to be brighter. So it appears to be closer to us. So we would have a biased estimation of the distance to this black hole system. And it also turns out that this would also affect our estimation of the true intrinsic mass of the system. And it is another correlation because the gravitational redshift and the mass is correlated. If you have any, I'm not going to describe this now, but we can come back to the question and answer session. So to summary, this lensing would enable us to see such distant object, but we would have biased estimates of their distance. We would estimate them to be closer, and we would also estimate their masses to be larger. So we would have a biased estimation of the mass of these black holes. And some authors also, in fact, argued that these massive black holes that LIGO have seen are a bias caused by the gravitational lensing. I told you that this massive black hole that LIGO have seen was a surprise to most astronomers. But the near consensus in the broad community is that this is a very stretched argument, because if you want this to be true, this claim to be true, one has to fine-tune a lot of things, the star formation models and binary black hole distributions, and the mass functions of black holes, etc. I mean, and you have to have really contrived situations to explain this through this lensing explanation. While nothing is stopping us from using a simpler explanation, that is that the true mass function of black holes include binary black holes with larger masses also. And also, if these lensing events were so common, you should have seen other tail signatures of the lensing, such as the multiple events, etc. Anyway, there are some interesting arguments going on, and for example, this Scientific American article has some interesting popular summary of what is going on in this field. So that's why I'm coming back to the multiple images, because that is a real telltale signature of gravitational lensing. But while this is actually quite easy to detect multiply lensed images of distant sources using optical observations or radio observations or X-ray observations these days, because these observatories are so sophisticated now that the signal-to-noise ratio of these observations are millions or tens of thousands. And while in the case of gravitational wave astronomy, we are in the infant stages. So the signal-to-noise ratio of our observations is of the order of 10 or 20. So it's very difficult to identify multiple images or multiple imaged copies of the gravitational waves. The problem is to identify a handful of lensed gravitational waves among hundreds or thousands of unrelated binary black hole merger events in let's say a year worth of LIGO data. And that's like a needle in haystack problem. But the clue is to look for signals that are similar in shape. So this is sort of similar to the spectroscopy, right? The way to identify, to establish that two images are the lensed images of the same galaxy. What one would do is to compare their spectra. So in a similar way, gravitational wave observatories data also, you can look for signals that are of similar shape, and they're coming from the same location in the sky. And also, the time delay between these multiple copies should be consistent with the time delays that we expect from the non-distribution of lenses, because we know the distribution of galaxies in the nearby universe, and we can predict the distribution of time delays within multiple images. But the whole enterprise is challenging because of the low signal noise ratio. So at our group, we developed a Bayesian model selection method that basically formulates this problem in a more rigorous way. So what we do, for example, is to, from any pair of gravitational wave signals, you have two hypotheses. One is that they are the lensed copies of the same merger, and another hypothesis that they are just completely independent binary black hole mergers. So from the data from these two events, you can calculate the odds ratio between the two hypotheses. And it turns out that this odds ratio is the inner product of the posterior distributions of the binaries parameters, source parameters that we extract from the data. And posterior distributions are some kind of a conditional distribution of the source parameters, like their masses, their spin angular momenta, etc., of the binary black holes, given the data. And if these signals are copies of the same signal, then intuitively we expect that they should correspond to the same binary black hole masses, same location in the sky, etc. So we could more rigorously formulate this and write it in terms of a Bayes odds ratio. And similarly, we can also use our understanding of the distribution, the expected distribution of the time delay between events, because given a distribution of lenses and a given distribution of black holes, binary black holes in the universe, we can do an astrophysical simulation and predict the distribution of the time delay between multiple images. And here is an example of this calculated time delay. And if they are lensed, for example, which is the red distribution or the blue dash distribution, the CN dash distribution, they typically have time delays of the order of an hour or a few hundred hours. While if you look at a population of unrelated events, they would just follow some Poisson statistic, and then the distribution would peak towards thousands of hours or tens of thousands of hours. So that would give us a way of distinguishing between these true lensed events and unlensed events. So using these tools in hand, we in fact searched for evidence of lensing signatures in the LIGO Virgo data so far during the first two runs. And the conclusion is that so far we find no evidence of gravitational lensing in the first in the data in the events observed during the first two observing runs of LIGO Virgo. So this plot is some way of assessing the significance of pairs of events. Since there are about 10 pairs, there are 10 events, binary black hole, there are 45 pairs. And this plot shows the evidence towards lensing. So there are two measures of the evidence towards lensing. One is based on how consistent they are in terms of their signal shape, which is the y-axis. And the horizontal axis is how consistent these two are to the lensing based on their time delay the observed time delay between two events. So most pairs, and each red dot here is a pair of events. For example, 170104 and 170814 means the gravitational wave signals observed during those days. And it only shows this most loudest events. Most events are very, very small, such likelihood ratio. So to summarize, currently there is no significant evidence that suggests that any of the pairs of events are lensed. One could also ask how likely, assuming a population model of binary black holes, which involves some assumed mass distribution and assumed distribution in the cosmological redshift, how likely are a bit involved, but again, to summarize, our conclusion is that one does not need to invoke lensing to explain the mass and redshift distribution of the observed events. One can explain them using simpler explanations. So, and because this lensing would be a remarkable discovery and an exceptional discovery, we will need an exceptional evidence, which we do not have. to claim for lensing. So currently, we do not see any exceptional evidence of lensing yet. So these sort of things were similar to the lensing signatures in the electromagnetic waves. But gravitational wave observations, possibly for the first time, would also enable to see something that we have not seen before, which are wave optics phenomena due to lensing. So, for example, when the wavelength of the light or gravitational waves becomes comparable to the gravitational length scale of the lensing object, then interesting wave optics phenomena can happen, like diffraction and interference. This is similar to the diffraction of two light beams coming from like a double slit. So you slit width comparable to the wavelength of light to see some interesting diffraction pattern. So similarly, if the gravitational radius or the gravitational length scale of the lens is comparable to the wavelength of gravitational waves, which is of the order of 100 to 1,000 years, then one could see some interesting wave optics effects. And this would deform the observed signals, and one can calculate its deformation, and one can look for such signatures in the observed signal. So here is again a cartoon version. This gray background chirping signal is an unlensed image, and the red and black shows how these waveform would be deformed due to the wave optics lensing by a point mass object, which is about 100 solar mass, which is the red one, and 1,000 solar mass. So you could see some very interesting beating patterns. And it is easy to model these and one has to introduce parameters like the lens mass and some impact parameter, etc. And one can look for the evidence of such deformations in the observed signal. And again, we did a search for such evidence of lensing signatures in the observed signals, and so far we do not see any overwhelming evidence of lensing signatures in these observed events in LIGO and Virgo. But as I told earlier, because of the sheer number of events that we are expecting in the next few years, we are fairly confident that we will make the first observation of lensed gravitational waves in the next few years. So why is it a big deal? One would imagine that just like the lensing observations of electromagnetic waves have emerged to be a powerful tool for astronomical and cosmological exploration, gravitational lensing observations of gravitational waves will also evolve in such a way in the next decades. And we are only starting to think about what are the potentially interesting applications of its lensing of gravitational waves. And we already have some very interesting ideas. One is that the multiple imaged gravitational wave lensed events would enable a precise localization of the merger event. And this is something very difficult to do using purely gravitational waves. And for example, if you compare, these are some of the reconstructed locations of the gravitational wave signal that we can reconstruct now. And they span several hundred square degrees in the sky. Even in the best case with LIGO India and like a 5-detect network, our ability to localize a gravitational wave signal in the sky is of the order of a square degree or few square degrees. And even in this 1 square degree, there are millions of galaxies in the sky. And it turns out that if you have quadruply imaged gravitational signals, using the time delay and magnification ratio between them and combining them with some optical observations of host galaxies, one can actually spot the host galaxy of this gravitational wave event, which is a remarkable thing, because currently, although we are observing these hundreds of or tens of gravitational wave events from binary black holes, we do not exactly know how nature produces them. And the understanding the host galaxy and the host environment of these binary black holes would be a very key ingredient in our understanding of this astrophysical processes. One can also do some very interesting tests of fundamental physics using lensed gravitational waves. This is the work done by ICTS graduate student Srishti Goyal. And here the idea is that if you have, let's say, two copies of the same gravitational wave signal, you're basically observing the same event with twice the number of detectors. And the key aspect is that, according to Einstein's theory, gravitational waves have two polarizations. And one interferometric detector basically measures one linear combination of the two polarization. And if you now measure two copies of the same signal with a time delay of, let's say, a few hours, then the detector would have rotated because of the rotation of the Earth. And in the second image, you would be observing a different linear combination of the same polarizations. So you have two equations to solve now, and you can uniquely solve for these two polarizations. And so basically, it is like doubling the number of detectors to observe the same source. So if you have a lensed event that produces multiple images, you're basically doubling the number of detectors in the international network of gravitational detectors. And this would significantly improve our ability to understand the polarization content of gravitational waves. And sometimes you can also ask whether this polarization content is consistent with Einstein's theory, because there are other theories of gravity that predicts extra polarization modes. Similarly, the wave optics effects that we can observe in the gravitational waves can also be used to constrain the fraction of compact objects that form dark matter, similar to what electromagnetic observations were able to do. But here, even a non-observation can be very useful, because, as I said earlier, if you stare at a lot of cosmos and you do see no microlensing effects or wave optics effects in any of these hundreds of signals, that you can use to put an upper limit on the abundance of compact object in between us and the source. And that basically can be used to constrain the fraction of dark matter in the form of such compact objects. And it turns out that, so this possibility has been heavily constrained in different mass ranges of such compact objects. But it turns out that LIGO is uniquely posed to put constraints in a region of mass space in the form of these compact objects, which is not heavily constrained by other observations. So LIGO is able to put constraints on the fraction of compact objects forming dark matter in the mass range of about 10 solar masses to a few thousand solar masses. So let me stop here, and I would like you to take some points home. One is that the gravitational lensing observations began as a way of testing the validity of Einstein's theory. That was the motivation of Eddington and his colleagues. But eventually, it became a powerful tool for the probe of astrophysics and cosmology. Similarly, gravitational waves also. And now it is becoming a really unique branch of observational astronomy, bringing up a wealth of information. The first observation of gravitational lensing of gravitational waves is expected in the next few years. It was doubly Einstein. The gravitational waves themselves are a phenomenon predicted by Einstein, theory of relativity, and now we are going to see a next sort of effect of lensing on top of these gravitational waves. And one would hope that this would be a very, very powerful tool for astronomers and cosmologists in the coming decades. And there are already indications of the same. So let me stop here, and thank you very much.
Thank you, Professor Ajit, for the talk. It was a wonderful talk. So I'll just quickly go to the questions now. You
Sure.
can have some water.
Yes, thank you.